So there are a bunch of containers that are part of STL. As you recall, STL has 5 main things: containers, which we're about to talk about here, and there are different types of them. Algorithms, you've got a little bit of exposure to some of those now, hopefully. Iterators, which are the way you walk around, which is the way algorithms walk through the containers. Functors, or known as function objects, and adapters. Those are the 5 main things that STL has. So let's talk about some of the containers. One of the containers is a vector. So a vector is a lot like a built-in C or C++ array, in the sense that you can allocate it dynamically, and you can assign things to its values, and you could read things to its values, and so on. But vector goes a lot further than the built-in arrays in C and C++, which are kind of lame, honestly. And it gives you the ability to grow them dynamically. It gives you the ability to do range-checked access if you desire. It figures out ways to do assignment, initialization. You can pass these things as parameters by value. You can delete them, and their memory is automatically released, et cetera, et cetera. So there's a lot of cool things you can do with arrays. The most common thing you do is basically index into it, just kind of like you do a regular array, as well as push back. And we'll talk about push back here in a second. It also supports something called random access iterators. There's different kind of iterator categories. There are 5: input, output, forward, bidirectional, and random access. We'll talk about all 5. And the random access is the most powerful. And what that means is an iterator has operations defined on it that are basically the same as you would expect with so-called pointer arithmetic, which is something else that you may or may not have been exposed to before, but C and C++ give you the ability to treat pointers and increment them and decrement them and do funky things to them. We'll talk more about that when we talk about iterators. They're very similar to C and C++ arrays, but they have more things going on for them. So here's a very simple example. We iterate through the command line arguments to the program, and we put them into a vector, and then we go ahead and we print the vector out to the output. And let's see if I can actually get this to work. Not sure if I can. There we go. Copy. Let's see if it'll go here. Hey, what do you know? It actually worked. So that's good. Let's go ahead and kind of format it a little bit. I'll show you what this does. So this program, compile it, and then we say a.out, and let's go ahead and give it something like this: hello world. So you can see when we run this thing, hopefully that's big enough. Let me make it 20 points. You can see it a little bit better there in the back. So when I run the program, as you can see, it prints out the name used to invoke the program. We'll look at where that came from. And then it prints out the parameters we gave to it. So it says basically hello world. Just for fun, let's see if I say so this is kind of funny. We basically take the source of the program and give it to itself as input. And so that prints out basically every word in the input as a command line argument. Yeah? Is that technically what? A quine. Let's see. Quines, I'm trying to think of the famous quine. It's like, this is, no, that's Ce n'est pas un pipe, and it's a picture of a pipe, right? This is not a pipe, but it's a picture of a pipe. Quine sentences, yeah, it's like self-referential, right? That's what you're referring to. I'm not sure if it's a quine or not. It's a good question. So here is the program. As you can see, when you run a program in C and C++, it gives you the command line arguments. Argument 0, argv is the argument vector. Argc is the argument count. And all programs start out with at least one thing. So argc is typically 1, and argv sub 0 is the name of the program, name used to run the program. So what we do here is we go ahead and make a vector of strings, print out the program name, and then we go through every one of the arguments, pushing this back into the end of the vector. And as you can see, we do the pushback operation, which inserts it one at a time from the back. It's kind of like pushing something onto a stack, if you will. And then we go ahead and we write out which project we have by taking I, which is a loop counter, and subtracting 1, because we're going to start from 1 but we want to start by printing out location in 0. So anyway, just a very simple example. This illustrates a vector in STL. Let's take a look now at a deck. A deck is much like a vector, the main difference is being that unlike vectors, where you can really only efficiently insert at the end, with a deck you can insert in the front. And that's because a deck is something called a double-ended queue. That's what deck stands for. And so the double-ended queue allows you to put things at the beginning efficiently and at the end. Another major difference between decks and vectors is that decks are typically implemented as non-contiguous chunks of dynamically allocated memory. Let's take a look at an example. If you Google deck, you will find a Wikipedia article that talks about a double-ended queue, and it's got a bunch of cool stuff in it. And down here, they have some interesting things. They have an illustration of a typical implementation of a deck. As you can see, a typical implementation of a deck is really kind of a map of chunks, where each chunk might be 10 items or 100 items or whatnot, and they start by growing in the middle, and they can grow outwards. And so when you reach the end of the chunk, it allocates another chunk and puts that into the map. And that allows you to be able to have constant time lookup and retrieval, but you can do things at the beginning and the end very efficiently. There's also another interesting article here that shows decks, and it shows you some performance consequences of decks. Here's just a couple things to look at that are kind of interesting. When you insert something into a deck, because it doesn't allocate the memory contiguously, as you allocate stuff in it, it takes about the same time to put each element in. If you're putting things at the end, and it grows. In contrast, with a vector, as you insert things into the vector and the vector becomes full, that fullness is the implementation details, not something you are concerned with. The vector has to stop, reallocate, grow, and then continue, much like your resize method that you have. So that's what's happening here. As it runs, you can see every once in a while it has to resize, so it takes longer to run in that particular situation. Here's another view of this. The deck is more or less constant time to insert things, or to push back things, whereas the vector has periodic spikes.
So for a vector, pushback makes it grow, and popback makes it shrink?
Pushback adds something to it. Whether it grows or not, of course, depends on whether there's enough memory to put the next item in. Popback pops an item off. Popback does typically not make it shrink. They do optimizations on vectors, kind of like what we did with our assignment optimizations, where once it reaches a certain size, it typically doesn't shrink unless you tell it explicitly to get smaller. There's something you can do to change the size of the vector through something called reserve. So this is an interesting article. If you poke around, you'll see that each of these approaches has benefits. One of the other nice things about a vector is when you remove something from a vector, it deallocates one piece of memory because the whole thing is allocated contiguously, whereas with a deck, it's typically as a sequence of chunks. So deletions take a little bit longer to run because it has to free them all up. Here's a fun little example using deck. As you can see here, we put a bunch of things into the deck, and then we go ahead and we're going to write the output to the standard output. And I'm going to copy this example and illustrate it for you so you can see how it works, because it's kind of cool. Let's go ahead. We're going to go ahead and pop over to Visual Studio this time, because Visual Studio has more powerful support for this particular mechanism we want to look at. All right, so let's get rid of those guys. Hopefully, compile this thing. We'll see. Yep. All right. So the result of this is 1, 2, 0. And as you can see, what we do is we go ahead and make a deck, and we put a 3 at the end. We put a 1 at the front. We use an iterator factor we'll talk about later to go ahead and get ourselves an iterator to the beginning, and then we skip over it, and we put a 2 after it, and then we put a 0 at the end, so that's why we have 1, 2, 0. And then we do something really funky. Excuse me. And let's go ahead and take a look at this, because it's kind of fun. So what we're doing here is we're using the STL copy algorithm. And what we're doing is we're going to copy from the beginning of the deck to the end of the deck, and we're going to write the output to standard output, putting a space between each of the elements. And that's why when we ran the example over here, we run this thing, you'll see it says 1, 2, 0. I could easily change this to be formatted slightly differently just by changing that. Then I run it, and now it says 1, 2, 0, but there's new lines between each of those things. OK, so what does copy do? Well, one of the cool things about Visual Studio is you can go over here and you can actually poke around in the implementation of copy, and you can find how it's implemented. And we may have to look around a little bit, and finally we find its implementation. Here's what it does. Copy is passed in two so-called input iterators, the beginning of the range and one past the end of the range. And then it goes into a loop, as you can see here. And while we haven't reached the end of the range, we're going to go through each element one at a time, and we're going to dereference the iterator, and we're going to assign that result to the third parameter copy, which is the destination. So that is expected to be something called an output iterator. As you might guess from input iterator and output iterator, you read from input iterators, and you can write to output iterators. So that's what that nomenclature means. So we go through here, each element at a time, copy the first to the destination, and then we increment destination, and we increment first by 1. Now, here's the really cool part. This algorithm doesn't care whether the iterators it's working on are iterators that come from an STL container, like dec, or vector, or string, or list, or map, or set, or whatever. It doesn't know or care whether it's doing that, or whether it's a container that you write. For example, you guys are going to be writing iterators for your queue that we're going to be doing, your list queue, your array queue, and your list queue. Or it could even be a built-in type. It could even be an array that's just a regular old vector, so or regular old C++ or C array. So if you take a look at this, for example, here we're using something that deals with decs. I could just as easily say int array, and let's go ahead and say 0, or how about 1, 2, 0, same thing. And then I could go ahead and say standard copy array, array plus 3. And then I could do the same gobbledygook stuff here that we'll talk about in a minute. And you'll notice here that this is now working on a built-in type. And hopefully, if I've done played my cards right, that should work the same. Oops, how about if I... Nope, I need to put an equal. There you go. So they print the same thing. The key point here is that the copy algorithm that we saw over here works identically whether or not it's working off of a user-defined type, like the STL dec, or a built-in type. We'll come back to this later. That's what makes STL so powerful, because the algorithms are agnostic or orthogonal or independent, choose your favorite big word, from the types of containers that they work on. I should say largely agnostic, independent, orthogonal to those things. There are some variants that are important. But for this simple example for copy, it's going to work for everything pretty much, and you can copy from one thing to something else. That also, by the way, is an example of pointer arithmetic. So although you don't see it in the code we have here, if you go look over here, you'll see that when this thing is passed a pointer, this is incrementing the pointer each time by 1. OK, any questions about that? That's copy. Now, the more interesting question, yeah?
What happens if your output, say your output was an array, and it was smaller than the input?
Great question. So here, let's look at a specific example just to make this point concrete. I'll tell you what we'll do. Int array 1, int array 2, and we'll say that this guy something like that, right? And now you want to write him to array 2. So what is going to happen here? Does anybody know? Well, clearly, bad things will happen, OK? Yeah.
Will it make it throw an exception when it's the third?
Probably won't throw an exception. Let's go have a little fun and see what different compilers do. Let's first see what Visual Studio does. Okay, it blew up, which is good. That's exactly what it says. Something out of range. That's a good answer. We like it when it blows up like that because that means that you're less likely to have surprises in your code. Let's try G++ and see what it does with the same code. All right, let's run that thing. What do you know? It just sort of worked, right? Sort of. It didn't blow up. Let's try this. Let's try running it with ggdb. And now let's say valgrind a.out. So that didn't really find it, did it, right? So that's a good example where the implementation or the tools that you use have an impact on the results that you get. So the best thing to do is to not write code like that. But if you do write code like that, you should try to use the right tools that will detect indices or things that go on beyond the range. The bigger answer to the earlier question was STL happily lets you do that. So it's up to you or your tool environment to catch those kinds of problems. Okay. Another container, so we use vectors a lot, Dex not so much. Another container is a list. A list is similar in the sense that it gives you the ability to insert things at various places. A list allows you to be able to insert things anywhere in the list very efficiently because it's a linked list. And with STL, the list is a doubly linked list. So that means it has a forward pointer and a back pointer, or a next and prev pointer, as they're often called in the literature. So that means if you want to insert anything anywhere in the list, it's just a simple rearrangement of pointers that are done for you by the list implementation. It also means that every node has 2 additional pointers to it. So if you don't like that, there's also a forward list that STL defines that only has one next pointer that goes in one direction. Yeah?
If it's just a linked list, how does that allow constant time insertion and deletion?
It doesn't allow, it allows constant time insertion and deletion, but finding where you want to go takes linear time. Right? So once you've found where you want to go, it's constant time to insert it, but figuring out where you want to put it may take linear time. I don't use list a whole lot, but it's powerful, and there's a bunch of things you can do with it. Here's some interesting things where you can reverse lists and do various kinds of stuff. We won't talk about those things right at the moment, but we'll come back and talk about that later. There are also, yes?
For assignment 3, will we be using the STL list?
No. For assignment 3, you'll be implementing, because you're actually implementing a queue as a circular list. But in this particular assignment, there's a variety of different things we're trying to do in this assignment. One of which is to show people that playing with pointers is tricky. So you will learn that. And if you used STL's list, then you wouldn't learn that. You just say, I'm going to use the STL list. It makes the problems go away. We're also going to be doing some other things like talking about the use of dummy nodes. We're going to be using iterators. So when you're all done, you'll have a really cool, very concise solution that has very few moving parts to it. It's going to handle everything properly. And you'll get a chance to learn how to do proper dynamic memory allocation with exception safety in a linked list or a pointer node environment. Other questions? OK. So those are the 3 main so-called sequential containers. Sequential because typically the order that they end up being in is the order you put things into them, like through things like pushback and so on. The next form of containers we're going to talk about are so-called associative containers. And unlike the sequential containers where you have this ability to have just put them in and the order doesn't really matter except the order you put them in, with associative containers, for the ordered associative containers, the order matters. And ordering is done based on something called a key. And a key is basically any type you so designate, because it's a parameter after all, where you define what it means to do comparisons. In particular, you define the less than operation. And so by defining less than, then it goes ahead and does everything else for you to order the appropriate way in which the associative container is managed. Now, there's 2 main types of associative containers, sets and maps. And there's two variants of each of those. There's a map or a set that has only unique keys, and then there's a multi-map and a multi-set that can allow duplicates. So that's the main difference. Multi-map, multi-set can have duplicate keys. Set or map, unique keys. That's one important thing. Another thing to note is that under the hood, maps and sets are both implemented using something called a red-black tree. And if you take a look and you go out and poke around on the internet and you type in red-black tree, you'll see a Wikipedia entry that talks about red-black trees. A red-black tree is basically a completely ordered, partially complete, balanced binary tree. And what that means is that no matter how many elements n there are in the tree, it's balanced such that the depth of the greatest branch is never more than log base 2 of n. So that's what it means to be a balanced tree in this context. So that means that insertion, removal, and lookup are all log n operations. So it's very efficient to do certain things with it in terms of asymptotic time complexity. Yeah?
This may be relevant, but why necessarily do they use red-black tree as opposed to other self-balancing trees like an AVL?
Good question. The question was, why do they use red-black trees versus AVL trees? I don't know. Just probably whoever implemented it knew how to do red-black trees or something like that. So that's just a little trivia bit for you. You don't have to really know the details of that. So here's an interesting example that illustrates the use of a set. And it'll show a couple things that I want to kind of illustrate to you. So let's go ahead and copy it, and we'll paste it in over here and run it for you. All right. See if this compiles. Oops. Need to include assert. How about it? There we go. All right, so you can see it prints out a bunch of numbers, all of which are unique. So 5, 10, 15, 20, 30, 40, 50. And what it does is it goes ahead and it makes a set, and then it goes through the set and it inserts a bunch of elements into it from 10, 20, 30, 40, 50. So it puts those 5 things in there. And then it goes and it tries to insert element 20. Well, element 20 is already there. Because this is a set and not a multi-set, that operation will fail. And what it means to fail in this case is you'll get back something called a pair. A pair is a very simple data structure. It has a first and a second. So it's basically a tuple with 2 fields in it. The first field in the tuple that's returned is basically an iterator that says where the item is that you tried to insert. The second field is a Boolean that says whether you inserted successfully or not. So if the item was not there, then the second parameter is set to true because it did indeed insert it, and you get back an iterator to where it was inserted in the red-black tree. If it was already there, as it is in this case, what happens is it goes ahead and gives back a false because it didn't insert it because it was already there, and it gives you back an iterator to where it was. So no matter what, you get back an iterator to where it was, and then you can go ahead and figure out if it was there or not. So of course we want to assert that it was false because it was already there. We now go ahead and put some more things in, some more elements into the set. And notice we try to put a 10 in. A 10 is also a duplicate, so that will ignore the 10. It'll only go in one time. And then go ahead and print the results to the output. Let me show you a couple fun things here. First of all, with C++11, you can now use the so-called initializer range syntax. So let's go ahead and fix this so we can take advantage of that feature. So here, I can now do this. I can go ahead and actually give it a range instead of having to create a separate variable. So I can do that. That's kind of cool. And now let's go ahead and change the set to multi-set. Hopefully, oops. Oh, hold on. Yeah, we'll come back to that later, because I don't want to waste time on it. But if we had used a multi-set, here, let's do this. There we go. When we use a multi-set, you can see now that we can have 2 copies of 10. So multi-set, duplicates, set, non-duplicates. Any questions about set? Pretty useful data structure, but the most useful data structure in STL is actually the map. Here's the pair we were just talking about. It basically is just a tuple that has a first and a second. Real simple. All right, let's talk about the coolest container of all, though, in my estimation. This is the STL map container. And a map is basically a mapping from keys to data, or keys to values. And so it's actually a template, a parameterized type, that's parameterized by multiple parameters, one of which is the key type, and the other of which is the data. So let's take a look at an example. This is one of my favorite examples in all of STL. And let's go ahead and implement it over here. And let's see. All right. There we go. OK. So this goes ahead and it type defs a map to be a string to int mapping. So it's mapping string key to int data, or int value. And then down here we define my map, which is a type def for this thing. And then we're going to go ahead and read the contents into the map. And here's what it's going to look like. Let's go ahead and make that slightly easier to read. And then I'll go ahead and run it. Hopefully it'll compile, which it does. OK, so we're going to basically give it some input. Let's go ahead and give it itself as an input. We'll do another quine. So here we go. As you can see here, what it does is it prints out every word it's given from the input along with a prefix that says the number of times that word appeared. Maybe it's a little easier to do it on something besides input. Let's just give it let's just run it. So we can say, now is the time for all good people. Oops. Yeah. OK. So you can see it basically takes the input and it tells you how many times each thing appeared. So that's what the program does. Very simple program. Let's go look at how it does it. That's what's more interesting. So what it does is it reads in every input one word at a time as a string. And then it says, my map, because that's the type, or that's the object, it takes the string you gave it, which is a word, which is a string. It indexes in there using that as the key. And it increments by 1 the value that's stored in that location. And all the values start out with 0. So every time it uses the string as a key, it indexes into that location in the associative array in the map and increments that by 1. And then when it's all done, it goes for every element from beginning to end, and it prints the element out. And I want to kind of show you a couple things about this. This is kind of cool. So first of all, this is the ForEach algorithm. And if you were to look at this thing over here, let's go look at ForEach. So here's ForEach. And you can take a look. Whoops. Yeah. Here's the ForEach algorithm. It goes from beginning to end of the range. We just saw what the range was. It's the elements that are in the map in this case. And it calls a functor, sometimes called a function object, on every element in that range, one at a time, passing in the value that the iterator is pointing to at that particular point. So that's what it's doing. It's going through this particular map, and it's calling a functor and printing out the results. So what's the functor? Well, the functor is defined up here. The functor is defined as a struct that has an operator function call method overloaded on it. That's what a functor is in C++ and STL. It's a struct that has, or a class, that has a function call operator defined. There is a function call operator, believe it or not. That's what it looks like. And what it takes there is a const of the value type, a const ref of the value type of the map, which in our case is going to end up being this pair, this tuple, that has a first and a second in it, because that's what gets stored when you iterate through maps. The value type is a pair that gives you the key and the data, or the value. So that's how it goes ahead and prints it out. Now, there's a bunch of really interesting things going on here that I want to talk about. And this is something where I strongly encourage people to go back and watch the video if this goes by a little too fast, because it's really important and very cool. Let me put it all up on the screen at the same time. So you'll see here that ForEach basically iterates from beginning to the end of the range, and it calls operator function call on an object of type print. Okay? Now, what on earth is this thing here? What is print open close?
It's function that's part of the map. It's built into the map.
So one guess is it's a function. It actually is, you're close. Yeah. It's a function with no parameters. Not quite.
Kind of like an anonymous function, like from Java.
You're even closer, but it's not a function, but it is anonymous, yes.
Anonymous object?
It's an anonymous object. Very good. OK, now, I could have done this if I'd chosen to. I could have said print, because remember, print is the name of a struct, my print. I could have done that. And then I could have passed my print here. And if I did that, then it would do exactly the same thing. So you get the same result. However, I assert to you no self-respecting STL or C++ programmer would ever write code that looks like that. Nobody would ever do that. Instead, what they would do instead is they would take advantage of the fact that C++ and STL do value semantics for the parameters that are passed in. And instead, as was just mentioned, you create an anonymous object of type print that gets passed by value into the ForEach algorithm.
So why do we use functors instead of function pointers?
Good question. So the observation here is, why do we use functors and not function pointers? In fact, we could have actually done this, just to show you something else that's kind of cool. I could have said void print it and made this a function that would look like this. So now we have a function, no longer a functor, and so on. And I could have come down here and I could have said print it. And now that would have been passed as a pointer to function. And if we were to run this, whoops, you would see that it gives the same result. OK. So I can either pass in a pointer to function here, or I can pass in an anonymous object like that. Or I could name the object if I wanted to. There's actually some other stuff I could do too, but let's start with those two. I could pass in a pointer to a function. I could pass in an anonymous instance of a functor. Why would I ever choose one versus the other? What is a function? What does a functor give you that a function doesn't? That's I think the gist of your question. Maybe. Although it's a little bit more profound and deep.
Is it exception safe?
Exception safe. It depends on the implementation of the person who wrote the thing, whether it's exception safe. But it's neither more nor less exception safe either way. So that exception safety is not an issue. So here's another way to look at the question. What is the difference between a function and a struct or a class? That's a more interesting question.
A struct or class can have data members?
A struct or a class can have data members. Put another way, it can have state, right? So you can store things in here. So let's go ahead and have some fun here. Let's go ahead and add some state here. Let's say int count. And let's also add ostream os. And now let's make ourselves a constructor that takes an O stream and have it go ahead and say count set equal to 0, OS, OS. Okay? And now let's come down here and let's say OS, like that. And let's also say count, let's say plus plus count. What we've now added to this particular thing is a way of being able to count the number of times for each runs, and we can also control where the output goes, right? So those are some things we did. So now when we come down here, I'll split the screen so you can see both things at once. Here's the class. Now I can say print standard cout. All right, let's see if that works. Oops. What's that? Oh, yeah, duh. Let's see, it wants something else here. I'll tell you what I'm going to do. This is what I really want to do. I'm going to show you the state thing. We'll worry about the O stream later. I probably forgot. Oh, yeah. All right, let's just do this. Come on. Oh, duh. All right. Okay, now it should work. Okay, good. So now it's going to work. Now the question is, what do we do with this? Well, what we have to do with this thing is down here we have to say print p equal standard for each blah, blah, blah. And then we're going to say standard cout number of iterations equals p count. All right. So what it did, this is pretty cool. It said number of iterations 56. We'll assume there are 56 words in the program just for kicks. Let's see what it says if I do word count. Yeah, it's counting words differently. So what it's doing here is every time operator function call is called, it's going to increment the counter by 1. And what ForEach does, if you go back over here and you look and see what ForEach does, ForEach returns the functor that was passed in as a parameter to it. So you can get back whatever you did as a result of making operation calls, operator function calls, on that functor object. So this goes back to the question of how is a functor different from a function? To do the same kind of thing with a function, we would have to define global variables, and it would get ugly, and you'd have to pass state back and forth. It wouldn't be an object, because a function is not an object. But a functor is an object, and so any old thing you can do with an object, you can do with a functor. But it has operator function call syntax for it to be invoked in the circumstance that makes it look like it's a function call. Yeah.
When the most recent time here, is the print with the parentheses still an anonymous object?
Ah, good question. So here's what's going on. Yeah, that's a great question. So here, we're making an anonymous object, and we're passing it in as the third parameter to ForEach. If you go back over here to ForEach, you'll see that's the method that's being passed in here. So this anonymous object is being created on the stack, passed in to the ForEach algorithm. Now we've got it here. We're making calls on it there. Each one of those calls, of course, is actually going up here and calling this function, which is incrementing the count by 1. And then, when we're all done, it's returning that functor as the result of the ForEach function. And now we're just stashing it away. So it started out anonymous. We called ForEach on it. Internally, it made the function call each time through. And when it was done, it took that object and passed it back. We grabbed it at that point, named it, and then did something to it. We could also do this, though. I think this might be another question you're asking. This is even more interesting. We could say, so what we did in that case is we actually call the ForEach algorithm. The return value comes back as the functor, and then we just went ahead and grabbed the appropriate field out of it and used it as the result right there. So it was never named at all. It was created anonymous. It went through the ForEach algorithm. The result came back, and we grabbed its count. Now, is that good code? Maybe not. But you asked the question, so I gave you the illustration to show that you could, in fact, do it. Yeah?
In the previous way you were doing it?
Yeah.
Were you doing an assignment there, or were you actually?
Yes.
Okay, so
Sorry, I was doing a it was a copy constructor basically, but I mean it was taking the result of this thing and it was creating a new object called
right. So, but it
P.
was so you had this that first object.
Yeah, let's go ahead and I'll show it to you so you can ask questions in the context of what I was showing.
Right. So you make that anonymous object.
Yep.
Once you basically dump for each loop, and then you're using the assignment operator. And
Yep.
setting that anonymous object.
Copy constructor, but yeah. The key thing to remember is in STL things are passed by value. So we get back a copy of the thing that was anonymous. This thing up there, print up there, is anonymous. It gets copied into ForEach. It's used in ForEach for every time it goes through the iteration. When it's all done, it makes a copy of that and gives it back as the return value for ForEach. So the copy constructors are getting called at the appropriate times.
What if your functor is like really big and you don't want to pass it by value? Is there...
Then you'll apply a pattern. So the question is, what if you have a functor with a lot of state? I think that was your question. You don't want to pass it by value. You would most likely apply a pattern like the bridge pattern we'll talk about later in the class in order to have a pointer to the object that gets copied and then do reference counting and other cool things to manage the object dynamically. Yeah, good question.
Why in the last example did it print the count? Like it printed out all the words in that the count is and then the count. Like that.
Oh, so every time it goes through the ForEach call, it's calling up here, which is printing the contents of the vector, of the map. Right? That's what that stuff's doing. And then when we're done, I just had a line, whatever it said. I just said standard cout number of iterations equal, and I just said p count. So that's just because I wrote it there.
But when you crammed it all in the cout,
Uh-huh.
it still did that.
Yes, right, because first it went and called the ForEach algorithm, which goes through each element in the map one at a time, calling its functor, which prints it out. And then when all that stuff is done, the return value of the anonymous print object comes back, and then we take the count of that and we printed that out. So that occurs at the end of everything. Yeah?
In the print function, it returns a my map value type. Is that defined in the map?
Yes. Remember, in STL, there are these things called traits. And so one of the things you have are iterator traits. We'll talk about those. Const iterators. We'll see those next class. There's also something called value type. For every container C, there is a value type trait, which is a type def of the parameter T that's used to parameterize the thing. Now, for a map, you have key for value for the key and D for data or whatever. So value type is a pair of key data. And the key is actually a const iterator for reasons that'll become clear when we talk a little bit more. Okay, what I want to do now in the remaining time is I want to go over your programming assignment real quick. But we at least got through the bulk of these things. And so we're ready on Wednesday to start talking about iterators. So this is good. This will get you ready for your next assignment. Okay, speaking of assignments, here is the web page for the class. And you can see that the next assignment is up here. It's got the due dates on it. It's got the shells. What you need to do, if you read the assignment, which I'll go over real quickly, is you need to go and download the shells. And first thing I would recommend doing is creating a new directory called assignment 3. Check the assignment for how to capitalize it or not. And put that in your SVN repository, subversion repository. Add the files, and you're just getting the habit of doing this. few people are still having some problems. If you have problems, let us know right away so we can get this stuff fixed. You really got to know how to use Subversion. Makes things way, way easier, even though there's a little bit of extra steps at first. So add those shells, commit that stuff as soon as you can, and then you'll be ready to go. And we're working on an automated regression test suite, just like we did for the other assignments, to help you test stuff. So what you're going to do here is you're going to implement some queues, which have first in and first out behavior. So the typical operations on a queue are enqueue, dequeue, or put and get, or push and pop. I mean, they're different names, but we'll give them certain semantics that are defined in the shells. And you're going to implement two different kinds of queues. One is called a queue, and the other is called L queue. As the names may apply or imply, an a queue is a queue implemented with your array. So that's why it's important to have a working array. If you don't have a working array, then your a queue is going to be rather hard to implement because it's going to be doing strange things. There are invariably a few people who don't get their a queues, don't get their arrays working properly, and then they have really mysterious bugs that pop up when they do their a queue implementation. That is by design, right? The whole purpose here is to show you if you take the time to develop reusable assets that are properly tested and have good quality pedigree, then life becomes easier when you do more complicated things later. So that's really the purpose of showing you that. We can't unleash you hacking up the Android virtual machine or the Linux kernel. That would be too much at this stage. But we can do something simple, and this is a good example. So you learn to build on stuff that you already did. So the first one is AQ. We'll talk about LQ later. There's also some stuff here about how to learn about what iterators are and how they work. So what you're going to do basically is implement the key operations on the queue, but you're going to use an array that's managed as a circular buffer. And what that means is things can move around in the array. So as you go through it, as you insert or as you enqueue and dequeue the items, you wrap things around. Now, there's a little bit of subtlety there. It's actually really easy once you do a few things to get it right. The key thing to do is figure out how to move yourself through the array, wrapping around when you reach the end, and then learn how to write STL iterators for begin and end on a circular buffer so that it becomes really easy to use the STL algorithms in conjunction with your iterators. And some of this stuff may or may not make sense at first. As we go through iterators, you'll understand it a bit more. As you start looking at the assignment, you'll understand it a bit more. But the end result is when you're all done, your solution will be really simple. That's because you've layered it properly with all these other things and other abstractions. And there's a really valuable lesson to be learned by thinking about software like this. And it'll help build you up the skills that'll be more beneficial when you get to patterns. Yes, sir? Do you have a question? OK. So enqueue, dequeue, front, these things are going to check to see if the queue is empty or full, throwing exceptions if the preconditions are violated. By the way, unlike your array, your underlying array allows you to resize the array. We're not going to use that for this implementation. So that's additional functionality you can use for something else, but not for this. So a queue has a fixed size. You give it a size when you create it. You say, I want an a queue of size 100. And it gives you a circular queue of size 100. Take a look at the stuff. I'll talk a bit more next time about what a circular queue is. Hopefully you learned that in class. OK, just a couple more things real quick. So you'll also have to implement iterators, which are important to understand. And the undergrads can do a simple version. They just do forward iterators. The grad students get to do forward and backward iterators. So they'll have to do a bidirectional iterator.
I think the undergrad shells ForEach might have also have bidirectional.
OK, we'll take a look. I think it says you only have to implement a forward iterator. So if for some reason there is a bidirectional iterator, just do the forward one, unless you're inspired. If you do forward iterator, backward iterator is really easy. So do that. Next quiz, ask questions, come to class, work on your programming assignments, finish up the last stuff. Everybody should do very well.